So in the last video you have seen how to compute the equilibrium distribution of an irreducible DTMC that is finite and aperiodic. So now here we will discuss the reducible case. So which means we have a finite DTMC that is aperiodic and not irreducible, which means you cannot reach any state from any other state. And then you cannot use this simple equation system that we used before. Just solving this, let's say you have n states. Solving this doesn't work for the reducible case. It's a little bit more complicated. And in particular, for the irreducible case, when you could use this, the solution pi didn't depend on the initial distribution, so pi was independent of the initial distribution p0. And now for the reducible case, this one doesn't work anymore, and here you have is dependent on, so this is also no longer true. So we have a dependence on the initial distribution, and we have to analyze the underlying graph. So the first thing we need here is to formally define what a bottom strongly connected component is. So we have a definition of a bottom strongly connected component. So a set, let's call it T, of states is called strongly connected if for each pair ij of states, ij of T, states in T, J is reachable from I and vice versa. And in particular, you reach J from I only by passing through states in T. So is reachable from I, sorry, I should here, passing only through states in T. Okay, and of course vice versa, because it holds for all pairs in ij in T, so it also holds for ji. So you can go from j to I and from I to j, but always only through states in T. And now a strongly connected component, let's make this blue, called SCC, is maximally strongly connected set of states. So what does this mean? There is no superset of it that is also strongly connected. No superset of it, no proper superset of it is also strongly connected. Yeah, so maybe an example. So here you see two examples of DTMCs, and let's consider, let's say, this one here, this DTMC. So we have a strongly connected component, which is this one. And it's maximal because if I would, for instance, add this state, then I cannot go back from state 3 to these states, so it cannot be part of the component. And also if I would remove a state, then it's not maximal because, well, state 2 should obviously be part of this because you can reach state 2 from any other of the other, from any state here, and vice versa. So state 2 should be part of this. Yeah. So, and you cannot extend it anymore. Okay, let's move this down. We might need it later. So a bottom strongly connected component, which is called then a BSCC, is a SCCT from which no state outside T is reachable from T. Meaning, if we go back to the example, so the yellow component is not bottom because you can reach other states outside of T. Yeah, so this is not bottom. This here is bottom because you cannot leave it. And this here is bottom. Yeah, so this is a BSCC, and this as well. And this is only an SCC here. Here in this example, actually, what we have is that only this one here is bottom. Okay. So now listen very carefully, because I will now give an overview of how to proceed when you want to compute the equilibrium distribution of a DTMC that is reducible. So you have given DTMC, which is finite, aperiodic, and reducible. And you have given P0. Now, to compute pi, you perform the following steps. Step 1 is find all BSCCs. Let's call them B1 to BK in the underlying graph. Let's call it X. Step 2, compute the vectors PE1 to, or compute vectors PE1 to PEK. E stands for entering, or eventually entering, actually, of eventually entering the components. So these here, of eventually entering B1 to Bk. So how that works, I will explain later. So step 3 is the following. Determine the equilibrium distribution well, actually the equilibrium distributions pi b1 until pi bk of the components considered in isolation. Because if you consider a bottom strongly connected component in isolation, it's irreducible. It's an irreducible DTMC. Yeah? So you can compute it using the same strategy as I explained in an earlier video for irreducible finite DTMCs. Okay, so once you have this here and this here, you can compute the equilibrium value or the equilibrium probability of each state as follows. Then for state I, let's say I is in BL, the equilibrium probability P of I is given as follows. So you start in an arbitrary state. So take the initial distribution and start in state J. Then from J enter the bottom strongly connected component BL. This probability is given by the value for state J in that corresponding P vector, PEL vector, and then multiplied with the value of state I that I has in the strongly connected component BL. Yeah. So the idea is as follows. So you have a Markov chain, and you have an initial distribution. So you could start here with probability 0.5, and maybe here with probability 0.2, and maybe here with probability 0.3. So now you have to choose one of these three states to start with. Let's say we choose this one. Yeah, we start here. And let's say here is BL. And inside of BL, we have state I. Now what you do is compute the probability. I don't know, I mean, you can go through a large number of states. I mean, there is a certain probability to reach BL, yeah, via a certain path. So you have to consider all paths to reach PL. This is something I will explain in detail later when I talk about how to compute these vectors here. So you can reach it via a certain path, and the probability of reaching it is PEL of J, if this is state J. Yeah. And once you are here, you have here, for these states here, you have an equilibrium distribution PBL, and then you just multiply with the value that state I has inside this bottom strongly connected component when you consider this in isolation. You will see an example later, but first, what if I is not an element of one of the strongly connected components, the bottom strongly connected components, then the p-value of I, the pi value of I is 0. Okay, so now let's go through all 3 steps in detail. So by the way, this is of course 0 because you cannot reach any BSCC, and then in equilibrium, you're never in that state here in equilibrium. So therefore it has probability 0. Okay. Let's first talk about step 1. We have to find all bottom strongly connected components of the chain. This requires to run graph analysis algorithms. For example, there is, for instance, Tayan's algorithm that can do something like this. Yeah, it finds strongly connected components, and checking whether they are bottom is relatively simple. So I won't go into detail about this. It's really simple. Just check Tayan's algorithm. And then the next step is more interesting. How to compute these vectors here. And the third step, how to compute the equilibrium distribution of each BSCC. Well, this is rather easy. Once you have the BSCCs, you simply write an equation system. So that was step 3. For each BSCC, BL solve pi BL equals pi BL times. Now, this is now a transition probability matrix that restricts to the states in BL. Yeah? And of course, you normalize to 1. That's J. Yeah, so here this is a submatrix of P for component BL. Yeah, so just remove all rows and columns of states not in BL. Okay, so that was step 3. Now let's come to step 2. We want to compute the probability of eventually entering one of the components. So eventually entering means in an arbitrary number of steps. So this can be done by solving an equation system. So for step 2, solve the equation systems the following. You have to do it for each BCC, of course. So the following equation systems for each BCC, SCC, BL. And that looks as follows. So here is a vector that is recursively defined like this. So it is the probability of reaching component BL from state I. So the situation is this. Here's I, here's BL, and we want to compute the probability of reaching BL from state I in an arbitrary number of steps. So this probability is 0 if BL is not reachable from I. There is no path, right? Then it's 0. If there is no path. It's 1 if I is an element of BL, of course. Then we are already there, so we reach it with probability 1. So, and the other case is it's equal to the following sum. So I make a transition from I to state j. So I go here. And then from j, I reach BL. So I take the probability to reach BL from j and multiply it. I mean, I first go from I to j and then multiply with the probability of reaching BL from j. Yeah, so I just sum over all possibilities to reach BL via some other state in one, I mean, first one step to another state and then reach BL from there. So this I do for all j which are not an element of BL. And what I can also do is, if this is I can enter BL directly in one step. So I go to state j, which is in BL, with probability Pij. Okay, so the probabilities that we really want are the solution of this recursive equation. Yeah. And now this looks not really like a linear, well, it is a linear equation system, but we can write it in matrix vector form, then it gets a little bit easier. So what is this in matrix vector form? It's the following. This is E and L is equal to PEL times probability matrix, but transposed. Why is this? Because it's not inflow outflow. It's really, I mean, what you do is you combine these two sums to one sum, to sum over all j. Yeah, you can combine this. Write here Pij and here PEL of j, and then it's still correct, because if I'm already in BL, if j is an element of BL, then I have 1 here, right? So I can also take a sum over all states here and write this. That's then the same. And also, if state j cannot reach BL, then we have 0. I mean, we just must enforce this. Yeah, we have to enforce these two things, right? These two conditions, and then what remains is this relationship. Therefore, it's like this, together with the condition, with the side condition that PEL of I equals 1 if I is in BL, and PEL of I equals 0 if BL is not reachable from I. Yeah. So now I've here matrix vector form, and now I will show you. Well, the example comes later, but you have to believe me for the moment that this is correct, and that these two conditions here can be incorporated in, well, that the whole thing forms an equation system that has a unique solution. Yeah, that's the point. Okay. Well, let's do now a large example where we have a reducible DTMC and compute the equilibrium distribution of it with all steps that are needed. So the example that I'm taking is the one from here, actually. Okay, so here we already saw that we have 3 components, 3 strongly connected components. So 2 are bottom, this one is bottom, and this one is bottom. The yellow one is not bottom. So we have done already step 1, finding the strongly connected components, and we have 2 BSCCs. Anyway, B1 and B2. So the first thing we can do is compute the equilibrium distribution of the 2 BSCCs considered in isolation. So this BSCC here, the green one, is B1, it's called B1, and the red one is called B2. So B1 has a transition probability matrix PB1, which has, you have 3 states. So B1. So the first state is number 3, and it has a self-loop with a half. The second state is 4, and you can go with a half from 1 to 2. Well, it's from 3 to 4. You cannot go from 1 to from 3 to 8. Now state 4 has the probability a half to go to the first state, and a half to go to the last state and no self-loop, and the last state has a self-loop, and it goes back to state 4. You see here the symmetries, yeah, and actually if you plug this into MATLAB and solve the equation system, namely PB1 equals pi B1 equals pi B1 PB1, and you need also that the sum of the entries is 1, then you will find that the result is that all states have probability 1/3 in the equilibrium. Yeah, which comes from this, it's for each state there is, in each state you remain the same number of steps on average in the equilibrium. And this comes actually from this very nice symmetry that you have here, in this matrix. Okay, so for B2 we directly see that it must be a half and a half, because in equilibrium you alternate between 6 and 7. Yeah, in each step you make a change. Yeah, you change the state. So it must be pi B2 is a half and a half. And now the interesting question is, what do we get for the reducibility probabilities? So we have now 2 things to do. So that was step 1, that was step 3 actually, and now we need step 2. So for step 2 we have to solve this equation system here that I showed you earlier, together with certain side conditions, and they depend on what BSCC we consider. So in general, we would like to transform this into a linear equation system of the form AX equals B, as we always do. So we can rewrite this a little bit. So this is the same as if I have PE. I called it PE. Of course it has an index L, but yeah, okay, let's edit. So PEL, and here I have the matrix minus identity matrix equals, and then the 0 vector. You can also reverse roles. You can put I here and P here, it doesn't matter. And now we want the form AXB, so I would now transpose. So I have here transposed, and well, this is a 0 vector now as a column vector. And this is now the matrix A. Actually, transpose of this is the same as this, because P transpose 2 times is P, and identity matrix transposed is identity matrix. So this is A. And this we call vector X. And this is vector B, but, well, we will change it a bit to take into account the side conditions. You remember the side conditions were the vector should be 1 if we are already in the BSCC, and it should be 0 if it's not reachable from the current state. So I prepared this here already in MATLAB. So this is the P matrix of the whole chain, well, of the aggregated chain, sorry, yeah. And important, here, actually I should put this like this, then you can see it better. There are these 2 states. So actually this state, this row here, and this row here are the 2 rows that correspond to the 2 BSCCs here. And now when I compute A, I have this. And since these 2 states here had self-loops, and I subtract the identity matrix, I get zeros here. I get 2 rows with only zeros. Of course, then the rank of A is just 3, which means we don't have enough information to determine the vector X here. However, there are these 2 things, these 2 conditions here that we want to incorporate, and we will do it exactly in these 2 rows. We'll use these 2 rows to incorporate the condition that the vector is 1 if you are already in the BSCC that you're considering, and 0 otherwise, 0 if you are in the other one. So now it really depends on whether we consider the first BSCC or the second one. Let's consider B1, the green one. So for the green one, we do now, well, actually we do it also for the other. In the matrix A, we replace this row and this row by the identity vector. Namely, for the 3rd row, a vector that has a 1 on the 3rd position, and for the 4th row, a vector that has a 1 in the 4th position. So after this, let's carry this out here. Now A looks as follows. This is my new A. And you see I have here the 1 and here the 1. So when I have a 1 here, now I should show it to you. So you have here some entries, whatever, and here are some entries. And now in the 3rd row, you have 0, 0, 1, 0. Oh, it was 5 states. Sorry. The 3rd row is like this, and the 4th row is like this. So when you multiply this with an x vector, x1, x2, x3, x4, actually there is also a 5th row, doesn't matter. What I want to explain is that the 3rd equation will be of the form x3 equals b3. Yeah, so if you have this 1 here, you just need to put here for b3 the right number to say, this entry of the vector must be 1 or it must be 0, because we are already in the BSCC or we cannot reach it. So now we consider 2 cases. So first of all, replace 3rd and fourth row of A with unit vectors with corresponding. Yeah. So then for B1, this one here, we want to have x3 equals 1. So which means that B3 should be 1, and we want that x4 is 0, which means we have to put B4 to 0. And this is because from this BSCC you cannot reach this one. And this is exactly what I put here in the MATLAB code. This B vector here has a 1 in the third position and a 0 in the fourth position. And the other zeros are from here, yeah, from this equation system here. Okay, and now we can do our first computation. We compute, actually I want this one with B1. So that will be our first x vector. Sorry, I have to carry this out. Here I've done it. Okay, let's carry this out and see what's the result. So first here's B1. And now I want PE1. And here you see now the solution, which is the probability to reach this set here from the first state, from this state, from the second state. Actually, they have the same probability of reaching it. From the third, oh wait. Why is this 0? Yeah, from the third state is 1, of course. From the fourth state is 0. And from the fifth state is 0.2. So that's the solution for B1. And now for the second component, bottom strongly connected component, B2, we define a column vector, it's also called B actually, that has a 0 in the third position and a 1 in the fourth position because, well, here we put 0 and here we have to put, here we put 1 and here we have to put 0 because we want to compute the probability of reaching this set. So it's the same trick. And now look at the solution. So we get this. So from state 3 we cannot reach it. From state 4 it's 1, and from the others it's 0.6, from 1, 2, and from state 5 it's 0.8. Yeah? That's the solution. Okay. So now let us compute, based on this, let us compute the equilibrium distribution. So step 2, let's shorten this a bit. With additional conditions. This is what we did, and the result was that PE1 was 0.4, 0.4, 1, 1. Now I'm expanding this set and not taking the aggregated Markov chain. So this is for state 3 and state 4, which are both in the BSCC. 0.2 for this state, 0, 0 for these two, and 1 for the last one, state 8. And probability of reaching the second BSCC is 0.6, 0.6, 0, 0, 0.8, 1, 1, 0. So now you have these vectors here. Now, what the next step that you do is you multiply with the initial distribution. Actually, I didn't give you the initial distribution yet. So assume now the initial distribution is as follows. so you start with probability a half either in the first or in the third state. Yeah, so either here or here. Right? Yeah, here. In that case, the probability of reaching, let's say, B1, so you multiply this, and you get 0.7. Yeah, because you have here 0.2 and here you have 0.5 from this. Yeah? And you multiply this with this. And similarly for B2 you get 0.3 from here. Multiplication of these two numbers. So now you have the reachability probabilities. So this is reach B1, which was state 3, 4, 8. And this is reach B2, which was state 6 and 7. Okay, and now finally we can put it all together. The pi value of state 1 is the same as the one of state 2, is the same as the one of state 5, namely it's 0, because these three states are not in a BRCC, so they have 0 as equilibrium probability. For the state 3, and also for state 4, and also for state 8, we got a probability of 0.7, reaching it, multiplied with a third equilibrium probability. You remember? It was somewhere here. Where did I do this? Here. Yeah. So here's that vector. So times a third, that's the solution. And finally for pi 6 and pi 7, it must be 0.3, reaching the second BRCC multiplied with a half for the equilibrium probability of that BRCC, well, of the states of that BRCC considered in isolation. And this is the final result.